So I'm going to tell you a little bit about how TigerBeetle handles upgrades and why TigerBeetle's hand keeps upgrading the way it does. So first, and though you don't know about TigerBeetle, it's a high-performance financial transaction database written in Zip. It's fully open source, Apache 2 license, ready for production workloads, and it serves high-volume traffic for customers around the world in production right now. Zig itself is a new systems programming language created by Andy Kelly. It does a lot of cool things, but probably the most important to know for this talk is that it allows us to easily build TigerBeetle on a single binary on Linux, Windows, Mac. And it comes with great cross-compilation out the box, so you can build your Linux binary from Mac, or you can build your Windows binary from Linux, no problem. Now, TigerBeetle itself is a database that has a fixed double entry counting data model. So the double entry counting data model is actually baked into the database itself. And we don't use SQL. We can do this for a few reasons. Mainly the tight problem domain, financial transactions, debit credit. In TigerBeetle, there are accounts and there are transfers. A transfer debits one account and it credits another. I'm leaving out a few things here for sake of simplicity. It does do a little more than this, but this is sort of the meat of it. This is simple double entry accounting. This is what was used by the Venetians, or invented by the Venetians rather, hundreds of years ago, and you might have learned it in high school. If you're not familiar with it, imagine a system where every money movement is recorded twice. So one part shows where the money came from, another part shows where it went. By baking this into TigerBeetle, you can provide a path guarantee. No money is created or destroyed by accident. If you move 100 around from Alice Kebab, double entry account to make sure there's an equal and opposite effect. You can't simply end up with money appearing under the couch. That's then coupled with performance in the hundreds of thousands of transactions a second, deterministic simulation testing, major storage fault models, and built with static memory allocation for good measure. So you'll deploy TigerBeetle replicas, that's what we call a single copy of TigerBeetle running on a machine, into a cluster, which is highly available as a whole. Replicas might come and go, but the cluster is forever, or something like that at least. TigerBeetle doesn't scale horizontally, it's important to know. Scaling horizontally, adding more replicas to TigerBeetle actually slows things down slightly. It's done for redundancy and for fault tolerance, not for improving performance, not for sharding. In a usual deployment, we'll run 6 replicas across 3 availability zones or so, and they'll all keep in sync automatically. This means that you can move somewhere, asterisk, around 3 machines, and everything will continue working without any interruptions or manual edge required. This is powered by view stamp replication consensus, and the clients also participate in this consensus. The client can speak to any replica, not just current primary. A quorum of replicas determine the order of every operation and giving us a strictly ordered log. Response is only ever returned to a client once it has been acknowledged by the quorum, and this is pretty different from how things like standby SQL replication, if you're familiar with that, might well. This log is then coupled with a state machine. So you now have a very fancy sounding term, a replicated state machine. It's actually an extremely simple concept. All the log is a list of events, and the state is the result of those events being applied one after the other. Like, you could almost think of this as, in the traditional SQL sense, as sort of your list of SQL queries. They go into the database, and the state is the table after you've applied all of your SQL queries. If you have the full set of queries and that order, you can reconstruct the state exactly. If you have the state as of 5 queries ago, you only need the last 5 queries to recreate the state. Now, in SQL, it's a little bit trickier than just what I said because of things like rand, non-determinism, and the like. So in TigerBeetle, we make sure that our state machine, the path that transforms the vase into the state, is fully deterministic and identical across all replicas. Remember, these are different processes running on different machines. When running the same operation through the state machine, it produces the exact same byte-for-byte output. Now, this means that you can actually even look in the TigerBeetle data file on different machines and same locations in the data file, barring a few special cases, you will have the same data. This gives us very strong guarantees around things like integrity, as well as the ability to synchronize data between replicas should that be required. Say if hard drive or hard drive, an SSD has bad sectors or something like that. So this might seem straightforward. So you can see sort of a little pseudocode implementation of part of TigerBeetle state machine over here. And you'd actually be surprised. This is closer to the actual implementation than you might think. But if you have some code over here that, say, just, add something to an amount, like, surely this is not difficult, right? You just don't change that across versions, and you won't have a problem. Your staple shouldn't be the same between different versions. Unfortunately, things are always more complicated. So if you kind of peer into that code, nice, simple, synchronous, straightforward code that everyone loves, there's a full LSM tree hiding behind there. There's async code, there's callbacks, there's IO, there's a whole bunch of things. And ensuring this all works together is manageable when you're dealing with a single version, unless you're doing something explicitly non-deterministic, guys. If you don't have a bug in your barriers, everything will work fine. Like, we have this test that tests this. We have deterministic simulation test, and we have fuzzers. We have asserts that will catch errors if we make them there in production by crashing rather than corrupting data. However, when upgrading this presents a problem. If you try and run two different versions of TigerBeetle together in the same cluster, the number of possibilities that explode, right? You could have version A with version B with version C, how do you test all those different combinations? So people who run and have designed their own similar architectures have told us that, oftentimes they'll replay tons of customer data to check that it results in the same state. And even if that goes wrong, they will, have to introduce code. If they had some drift, they'll have to introduce some code that kind of drifts the state back towards the correct stables. Ideally, what we're looking for is a guarantee that given operation from a log is executed by exactly the same state machine version across all replicates. One way to do this is simple. You can stop the whole cluster, put in a new version, and start them all up again. This is, if you think about a single process system like MySQL, this was kind of what you're doing anyway. This is also nice, but you've traded all of your testing, all of your simulation, all of your fuzzing for the consensus of myself, the operator, manually SSHing into machines. You're relying on me to check things out. Is the cluster healthy? Is there something going on? Like, also, best case, you're causing minutes long downtime. Okay. What happens if the power cuts out midway through this nail upgrade? Like, of course, by the way, I'm referring to recent backups in Spain and Portugal. What if my Windows laptop decides to install upgrades? My Linux laptop's GPU decides to stop responding. And no, the answer is not to use the MacBook. What if we could use the very same consensus and log that were built and tested so thoroughly to also handle buffering? After all, we're a database. Like, storing things durably is what we should be doing. So that's the solution we settled on. We decide when to upgrade through consensus and through block. That's great, and it handles the logical part of the upgrade. Now, an individual replica can know which version it should be on, but it doesn't actually help with getting the version there and running the right version. That's where multiversion binaries come in. So a little bit about the experience we use in TigerBeetle. One part that's really important is that TigerBeetle is single binary. It's kind of, I know Go popularized a lot of this, but if you download a TigerBeetle release and you extract it and you run it, there's one file in there, you run it, that's it. No shared libraries, no other dependencies. You won't get some weird error because you're running Red Hat Linux 6 from 1998 that's still somehow supported. It'll just work. Sure, we provide Docker containers that you can run it in Docker. So this is actually our recommended method of deployment. The fewer layers of abstraction is better. And TigerBeetle can be deployed a lot of different ways, right? Like, it's open source, so you can run it in Kubernetes, you can run it in Docker, you can run it in all sorts of weird and wonderful configurations. And having multiple files and coordinate multiple things there, it's just not a great experience. So, how do we get multiple versions of TigerBeetle to exist within a single TigerBeetle binary? Well, we do a few tricks. What we do is we actually go and when you download TigerBeetle from the release page, for example, you get a single file that contains each release from previous versions embedded in that current version. Like, these aren't special releases or anything. It's the actual past releases that have now been baked into the current release that you download in a platform-specific manner. So while Linux is our only production target, we also support Mac and Windows for development. We want to ensure a good experience on all of them. So even if deploying a cluster of 6 MacBooks to hold financial data for your central payment switch is not recommended, TigerBeetle should still work as well in Azure beyond macOS as it can. Of course, embedding files into binaries isn't something new. If you ever used like a self-extracting zip archive or a virus, they'd be doing this for ages. And there were a few ways of looking at this, or doing this that we looked at rather. We could build a different version of TigerBeetle's libraries and then like dynamically load them and have a launcher. We could embed the different releases directly. Zig provides something called @embed file. This is really cool. It allows you to pull in any arbitrary file into your program and then reference it like in your code as a variable. So almost like copying and pasting the contents into your source code, but the compiler does it for you. Or we could do it manually, modifying our own binary with the additional data that we needed. And this is what we chose in there. You want a direct control over how things were handled. So if you could also include backwards compatible data to actually speed up the upgrades. We also didn't really want to have a distinction between like a launcher binary that like launches TigerBeetle and then like the TigerBeetle binary that actually does the database stuff. So on Linux, this turns out to actually be relatively straightforward. Linux executables in a format called elf. And adding extra information to an elf file is really well defined. There's this tool called object copy that will do it for you. And it's how things like debug symbols and other goodies are included with binaries. We kind of do the same thing. We have 2 extra sections, one that contains all of our past binaries, one that contains a bit of metadata, and we use object copy to bake this into sort of one TigerBeetle binary. This allows us to parse that information back out at runtime and extracts the exact binary that you want to execute that corresponds to the version you want to execute and run it out of memory directly without ever touching the disk on Linux. It's very cool. For Windows, which uses the interestingly named PE or portable executable, even though they only run on Windows, and still contain every Windows program to date still contains this fun line: this program cannot be run in DOS mode. Anyway, this format is actually still relatively easy to parse and to use because all the data you need is contained in the header, so we can read out the header, use a few parsing routines that Zig provides to get the information out, and extract the correct version. Executing this is a little bit more janky than on Linux because Windows only has create process, doesn't have exec. You can't replace the process, you always have to start a new one. So this leads to a little bit of weird behavior when running from the command line, but it works. macOS, on the other hand, macOS. The file format on macOS is called MacO, as in like macrocystic. Unlike ELF and PE, it uses like the sequence of load commands and all sorts of weirdness rather than a simple header. And the actual tools like object copy just don't produce a usable executable if you try like modify the binaries in the same ways. So thankfully we had an escape hatch here. For Mac OS, TigerBeetle provides universal binaries. They run on both Intel and ARM chips. And it turns out that the universal binary format is much, much saner, where it's simple fixed size headers. And turns out we can repurpose those. So on Mac OS, we actually used some old esoteric architectures that had never had a Mac OS release to hide and implement Pi, to embed the binary data for past TigerBeetle versions. And they're full there because we have the data and the metadata for x86 and ARM respectively. Cool. So that was just a quick whirlwind through the actual theory behind it. Let's see how it actually works. Maybe like go as it go, but these. There we go. Cool. So I've got 4 terminals here. We're going to pretend that these 3 are just TigerBeetle replicas. So I'm first going to format them. And then I am just going to sort TigerBeetle on each one. Cool. So we now have 3 TigerBeetle replicas running. Very boring. Nothing is happening. You can see that they're all running on 0.16.64. So let's do something interesting. Let's delete the binary. You see what happens. So we delete that and start getting message that the binary does not contain the valid multiversion data because it doesn't exist. Okay, cool. Let's copy a binary back in place. See, I have codes before. Boop. I copied the same binary, the same 0.64. It knows that the file has changed, but there are no new mergers, so nothing exciting. So it's actually going to, I don't know, corrupt that binary for some keys. Scope and elf on shells. Right, and there we go. Binaries are contained. So that's pretty robust. It's actually quick messing around now and the dark, right? So just drop in a new version TigerBeetle. And it will detect, so it's detected over there that there's a new release available. And internally, it has coordinated the upgrade across the 3 different replicas. It's restarted once now to go to 16.65, and now it's restarted again to go to 16.66. And now all TigerBeetle replicas are running on the same version. And that is, in theory, how simple upgrades. You drop the binary and stuff. And so what are card bugs? Well, there are a few interesting ones. So a lot of this code has to do low-level operations directly. Things like reading in the file from this. If you're familiar with how Linux handles this, there is whenever you read in a file, the kernel might have it in its page cache. So this is sort of memory that the kernel uses to cache disk access to make it faster. There's also the thing where when you ask it to read data, it might not always give you all the data you asked for, right? It might give you all the data you asked for. It might also give you, say, you ask for a megabyte and it gives you half a megabyte. So initially, we just handled this as an error. We asked the kernel for a megabyte, it gives us half a megabyte. Just read again and ask it for the full megabyte. Turns out that it will repeatedly give you the same half a megabyte unless you explicitly tell it to move an offset forward past what it's given you before, because it'll give you the data that it has in its page cache every time. So this was actually the first bug in it, and this was very interesting to find out. There was, you read from the man pages, you're like, huh. Another one has to do with bounds checking. So Zig has a lot of nice features. So Zig has bounds checking, and Zig has overflow on integers is a panic by default. So if you try and say, add 1 to an 8-bit integer that is at 255, it will panic and crash your program. It won't wrap around to 0 or negative 127 or anything along those lines. When dealing with random data that's coming from the disk, this can be problematic because you might read in some data from the disk, and that might be, say, a valid 16-bit integer. or to get some might be a valid 8-bit integer, it might be 128. And then you read in some other piece of data from the disk, and it's, say, the number 4. And these two things by themselves are both completely valid. But now you need to multiply them together because you're working out an offset, something like that. 128 times 4 is 512. 512 cannot be stored in an 8-bit integer. So now all of a sudden your program crashes. Normally good, but in this case, not good. What did we learn from all of this? So sometimes you've got to drop down a level of abstraction. For us, that was manipulating binaries directly and using like the exec system pool directly and not relying on like standard application logic. Like you can't be afraid to look behind cursor and do things manually if it gives you the properties you need. The other thing was like, how can you leverage existing guarantees, right? We had this whole log, this whole consensus, this whole deterministic simulation testing, all of this work and frameworks around it. How could we use that to, how could we rely on all of the work that's gone into that for our upgrades? And then another one, problems just always lie at the edges, like every single time. If you, like every time something transitions from being, you know, like the boundary conditions, it's like fuzz those things nonstop. We thought our auth parsing was robust. I wrote a fuzzer for it. Probably took me around half an hour to write the fuzzer. It found like 5 bugs within the first, minute of running it. And then lastly, just like simplicity for the user. So in our case, like this was a lot of work to get these upgrades done, but now they're done. And everyone using TigerBeetle gets the benefit from them. So all the upfront work just got amortized by the number of people using it. So that's why you should use TigerBeetle, because it makes this work cheaper for us. Thank you.